Right, guys. So what we're going to talk about, two things. They're linked actually. The more important one of the two really for you is standard deviation. But in working standard deviation out, you work out variance first. Okay. So taking you back to all that stuff that we've talked about in terms of the distribution of data, we've got two things that we might consider. We've got the measures of central tendency, which are what? Mean, median, mode. Okay? That would enable you to summarize. That's what happens when someone studies.
No,
You want to summarize a whole data set with one number, which enables you to do a very good what? Why do you work out the mean of two data sets? What do you want to do? Compare. Good. So to compare, the first thing you might do is look at an average. Once you've decided which one is the most appropriate, you do your comparison. Who's better, boys or girls? Don't know. Choose the mean, choose the mode, whatever, do a comparison by one number, but then you must look a bit deeper and look at the distribution of the data. Right? Now, what we're going to look at, variance and standard deviation, is concerned with the distribution of the data. More specifically, is we are looking at another word that you are going to have to get into your exploration. Okay, you need to validate conclusions. Okay, you need to validate your conclusions. Now, what that means is a calculation appropriate? Right? Is a calculation appropriate? Question mark. So, quite often when you're younger and you write a science project or a maths project, what do you end your project with? An evaluation. And what's in your evaluation? Give me an example of an evaluation. Was the method correct? Okay. In what way? So what would you write? Give me an example of a short line that you would write.
failure.
Pardon?
About failure, no?
You write about failure. What you would do next time, okay. So quite often you would read an evaluation lower down the school is, if I were to do this again, maybe I would do. My results might have been wrong because I didn't watch properly when I was doing the burning or whatever. Yeah, that kind of thing. Right? So an evaluation of how you went about your work. Now you need to scrap that idea. Alright? One thing you never write now is, I might have been wrong. Because if you write, I might have been wrong, guess what the examiner will do? Try and find out if you were wrong. And if you're wrong, you lose marks. You never suggest you were wrong. If in your final write-up for a piece of work, you can say to yourself, well, I might have done that wrong, go back and fix it. Alright? You are never wrong. Nothing you did was wrong, incorrect, done wrongly, given the wrong answer, rounded. It was never done wrong. That is one word you never say. However, what we do say is, was it appropriate? And you all know what appropriate means. Was what you said to your teacher appropriate? Yeah? You might say, but it was what I wanted to say, but was it the appropriate way in which you wanted to say it? So that's what we're talking. So with our maths, we've never done anything wrong. We don't do the wrong calculation. We have, however, a need to discuss whether I did the appropriate thing. So for instance, is the mean the right average to use? Would the mode have been done, would have been a better representation? We don't say, well, maybe I did the mean incorrectly. That just makes you sound stupid. Was the mean the appropriate one? Okay. And we need to look at distribution of data. So variance and standard deviation helps us with this situation. Right. Now, talk standard deviation. When we calculate a mean, because this is the focus for the standard deviation, is the mean. Okay? So we're looking at focus on the mean, and we are asking ourselves, was the mean, or is the mean, sorry, not the, an appropriate summary of my data set? Okay? That's what I'm asking myself. Now, bearing in mind, a mean is supposed to represent everything. We'll give you a couple of minutes. I want you to come up with a reason why the mean is not necessarily very good as a choice. We've already discussed this, but why would the mean not be a very good choice of average to summarise the data? Have a quick think, chat to each other. I'll come back in a minute. Okay, why would the mean not be a very good representation of the data set? Yeah.
It doesn't show the details of distribution.
Well, it never shows the details. It's one number. So it will never show it. But it could be good, it could be bad, but it will never show the details.
It doesn't show you the perspective.
But I could still use it. But that's not quite what I'm saying. So the mean will never show me the full picture, right? Because none of the details ever get included. It gets rid of detail and brings it to one number. But sometimes it is a good representation, and sometimes it's not. So that's what I'm asking for. What would you say?
If the values are like spread out enough, it wouldn't exactly give an appropriate value for all of them. Like it just takes like more or less than one. Whereas if the values were very similar, it would be good.
Did you read the book?
No, I didn't.
Spot on. Well done. So, basically that's it. The mean is supposed to represent the data. Now, what do you do to calculate the mean again? Add them all up, spread them out again. I kind of like the analogy of you've all got a bowl of ice cream in front of you. And some of you have got bigger bowls of ice cream than others. How do you get the mean amount of ice cream? You pour all the ice cream into one bowl, stir it up a little bit, and then spread it out evenly. Yeah? And that amount of ice cream you end up with is the mean amount of ice cream. Now, is that a fair amount of ice cream? Well, it depends, doesn't it? Because if you all had roughly the same amount of ice cream, but some had slightly more, some had slightly less, afterwards you would all end up with roughly the same as you had before, yeah? But what if a couple of you had barely any ice cream and some of you had a lot of ice cream? You'd all end up with a nice portion, but would it be a true representation of what you started with? No. The ones at either end, they'd be a long way away from what they had to start with. And that's basically what standard deviation tells us. Okay? So, really, simplistic terms, the standard deviation, all right, is the mean distance of each value from the mean. The mean distance of each value from the mean. Does that make sense? So what we're doing is we're actually taking every single point and we're looking at how far away it is from the mean. If in general all the points are a long way away from the mean, then that's bad. It means the mean's not very good. But if the points are generally close to the mean, that's good. We can use the mean. Do you understand how this could be therefore used as the mean is a good one to use?
So mean only works for the information is not that spread?
Yeah. Yeah. So what we're hoping for, is a small standard deviation. Okay. So that would make our mean a reasonable choice of average to use. If our standard deviation was large, it would suggest that we ought to go and use something else. Yeah? Now, I just want to draw your attention to that word small, the standard deviation. That word must be put in context. Okay? Okay. It must be relative to the values being considered. So it's kind of like a plus or minus thing. So if I say to you, right, the standard deviation for a cup of coffee in Starbucks is 20 millilitres. What does that mean to you, based on what we've talked about? Because we haven't done any calculation yet, so just checking whether you understand. So I said the standard deviation of the amount of coffee in a cup in Starbucks when they give you a coffee is 20 millilitres. What does that mean? On top?
Most cups in Starbucks are roughly like around that size.
What, 20 millilitres? That's like that much.
Oh wait, what did you say?
So the standard deviation of the amount of coffee in a cup in Starbucks when they've served you is 20 millilitres. What does that mean?
It could be plus or minus that.
Yes. So what they've done is they've taken all the cups of coffee been served, they've worked out the mean of that, and then they've said that a cup of coffee could be plus or minus 20 millilitres above or below that amount. Yeah, 20 millilitres above. Now, the question is 20 millilitres a small or a large standard deviation?
But what is the
coffee?
Ah, okay.
Like if it's 2 milliliters, the coffee is going to be very,
I
very
think we
big.
should-
If it's like 2 liters, it's small.
I think we should consider the mean.
Well, that's exactly what Michelle's just said, really. The mean will be relative to the coffee that I'm talking about. Because in Starbucks, you have big cups of coffee or you have smaller cups. So what am I talking about? So yes, if you have a 2-litre cup of coffee, 20 millilitres above or below, you're not going to notice, are you? But if I'm talking an espresso, little cup, 20 millilitres above or below, well, that's huge, no? That means there could actually be a 40 millilitre difference in the size of a cup of coffee. Again, in 2-litre cup of coffee, whoever has that, probably in America, right? That's neither here nor there. But in an espresso, that is huge, right? If I said to you, the measurements from Earth to a planet, right, has been taken by 50 different scientists. The standard deviation of their measurements is plus or minus 1,240,000 kilometres. Is that a large or a small standard deviation? Yeah.
But it was from planet to planet.
Yeah, but million kilometers. We
But-
did this in physics and
No, but times 10 to the power. Small.
How far is a planet that's 3 light years away?
Small.
Yeah, but compared to the planet in the solar system.
I didn't say that. So it's the same
Compared to
situation
what
as the
planet?
coffee cup. It depends which planet. But what I'm trying to get you to think of, some people go, oh, 20 millilitres, that's a really small amount, so therefore it's a good standard deviation. And 1.2 million kilometres is a huge amount. But depends what situation you're talking about. So I cannot say to you, this is a small standard deviation, this is a large standard deviation. You have to consider what it is we're talking about. Does that make sense? Yeah?
Would it be around 10% considered small? Or
Well, really, it's a value for you to decide whether you consider it too big or not. Yeah. It's just really, it's a comparison. So, to be honest, if you've got 2 data sets and one of them has a standard deviation that's significantly smaller than the other one, you would know not to compare them using the mean. Because one of them, the mean is fine, the other one, the mean is poor, so it's not a fair comparison. This is all we're really using it for. Okay. So, does that make sense now? All right. So let's have a quick look we're talking page 276, 277, right? We've talked standard deviation, we haven't talked variance yet, but we'll do that when we go through example 11, okay? So, we're not going to go through the full example, you'll see the process. So, in example 11, page 277, we have 30 farmers were asked how many farm workers they hire during a typical harvest season. Their responses were, okay, so 4 workers, 5 workers, so on. Okay, so we've got this frequency table there, and this is what we do. They've worked out the mean of all those numbers. Now you know how to do that, don't you? So 4 add 5 add 6 add 7 and so on. Okay. Now the mean has this value, that symbol, sorry, mu. You've seen that before. So the mean of this data set is 5. Right, that's what they've worked out. Okay with that? How do you do that, by the way?
X times on
X times F,
total.
divide by the total of workers. Yeah.
Over
Yeah. So basically, they know we've hired 30. There's 30 farmers. That's why we divided by 30. How many workers were hired in total? Should be able to read just from to calculate the mean. The mean is 150 over 30. So 30 farmers. How many workers? 150. So it's 150 workers in total. Spread them out equally between the 30 farmers. That's the average. In reality, some hired 8, some hired 0, but the mean is 5 each. Now, what we need to do is we're going to work out the standard deviation to work out, in general, how far away from 5 workers were the farmers. So, do you remember I said that the standard deviation is the mean distance of each value from the mean? So, just to go through, we've got some numbers here. I'm just going to write the first few: 4, 5, 6, 5, 3, 2, 8, 0, blah, 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 blah. Carry on. Now, to work out the standard deviation, first step was to work out the mean. We did that. We added them all. We divided. So it was 150 workers divided by the 30 farmers, gave us 5. Now, so what we do is this. We have to work out the distance from the mean. Right? So how would we do that? So it's each point. So we would do 5 take away 4 for that one. 5 take away 5 for that one. 5 take away 6 for that one. 5 take away 5. 5 subtract 3, 5 subtract 2, 5 subtract 8, 5 subtract 0, and we would carry on.
Where did this number come from?
Which one?
Minus 4 and minus 5.
4, 5, 6, 5, 3, 2.
Okay.
They're an example. Okay?
Do we need to?
So that's the mean minus the x value.
We do it the other way around. But do we need? Don't we just need the magnitude of how far away it is?
That's that, no?
Yeah, but we don't need the negative. So
Right,
say
well,
it's
this is what we're going to talk about.
this
This
thing.
is what we're going to talk about. So do you understand the whole, it's the mean, the difference between the mean and it? It doesn't really matter which way round you do it. Right, and I'll ask you why. How do we find the mean value of those distances? So obviously the distance is 1, 0. What's the distance for that one?
Minus. So 1.
Okay, right. It's 1, it's 0, it's 2, it's 3, it's 3, it's 5. Now, I want to just highlight this one and this one. Alright? Now, this is the important part. You told me that 5 minus 6 is 1, which is untrue. But you told me the answer 1 for what reason?
It's the distance, no? So
Exactly. It's the distance between the 2 points. Does it matter if it's positive or negative?
Yeah, because we're not talking about this.
Yeah, so we don't care whether it's 1 above or 1 below. We don't care. Alright? So actually, if I was doing this by hand like this, I would just write 1 down. And I would just write 3 and not negative 3. There is a problem, however. Mathematical function formulae must be written in a way that can be put into a computer. And a computer is dumb. A computer doesn't know that you want the positive, not the negative. Why can't I have the negative? Because what have I got to do to work out the mean distance? I've got to add them all up. Add them all up, and then once I've added them all up, I've got to divide by the total number of numbers, which is, in this case, 30 again, yeah? So, what would be the problem if I had a negative? So it's going to subtract the number, and I don't want that, do I? I can't do that. I have to have the distances, not a negative number. But again, I will say, your calculator, your computer doesn't know that. It would take away, which would ruin your whole mean. So, mathematically, what do the smart boffins do to get over that? No, you can't. You can't program a computer. You can't program a computer to do that. But we need a computer to do it.
Yeah, but then when you type in 5 minus 4, then...
No, but I don't. What I do with a computer is list all my numbers and click work it out. So, how do we get that to happen? So basically what we want to do is get rid of negatives. Okay? Would be a possible solution, but actually programming a modulus is the same sort of thing that we're doing now. You can't just tell the calculator to do, you had to program it to first do your modulus. What's the best way of getting rid of a negative? Squaring. So what we actually do is we do mean minus the value and we square it. So we square it, square it, square it, square it. Now, if we square that, we get the answers 1, 0, 1, 0, 4, 9, 9, 25. We add all those numbers up together. But what's that going to do to our mean? Square it. It's going to be too big.
So then we can square root.
So at the end, we just square root it. But what that's done is get rid of all the negatives, yeah? Make sense? Alright? So afterwards, when we've divided all of that by the 30, we then just have to square root it all. Does that make sense? Okay. So, having discussed that is what happens, let's have a look at standard deviation. Looks like that. Standard deviation of a population, right, is the square root of, and now you can understand why the square root is there, sigma, so the sum of x minus the mean, so they did it the other way round, squared. So you know the sum of is just adding them all up, yeah? All divided by n, the number of numbers we have. Now what's missing there is the I equals 1 up to n, yeah? You recognise that notation now, don't you? That's not a problem for you. Just means starting at 1 up to how n, in this case, would be 30. So does that make, based on how we went about it, does that formula make sense to you now? That's fine, yeah. Okay. Now that is standard deviation. Right? That's the standard deviation. Have any of you spotted what variance is? Yeah. Variance is standard deviation squared. It's just what you get before you do the square root. Right? And do you know what, to be honest, most of the time we always talk standard deviation, we don't talk variance. But what comes up in an exam question might be, oh, the variance is. So you would then just go, oh, well, I know variance, we need to square root it to get standard deviation. Now that, that's pretty much all you need to know. All right? Do you remember, have you noticed that symbol before? Calculator. Right, so, have you got your calculators with you? Because for you, all this handwritten stuff, not really that necessary. We can do standard deviation using our calculator. And we're going to do it like this. We go to Stat, Edit for lists, those of you that have done this before. Put a few numbers, put the first 8 numbers in. So we do 4, enter, 5, 6, 5, 3, 2, 8. Yeah.
How do you clear the list if you're on the side?
If you've got stuff in the list, go up to where it says list and press clear. Not delete, because delete will delete the list and L1 won't exist anymore. Okay? But press clear and then press enter. Yeah, now I've just deleted mine, so I have to do it again. 4, 5, 6, 5, 3, 2, 8. Let's just do that. 5, 3, 2, 8. Right, to work out the standard deviation of that data set, I go to, once my list is in, I go to Stat, Calculate, right? One variable statistics. I haven't got a frequency list, I've just got a list of numbers this time. So frequency list I'm going to leave empty. List was L1. Just going to press calculate. And you will notice, here look, is standard deviation. SX is also standard deviation, but you'll notice in the book we've got standard deviation of a population. SX is standard deviation of a sample. You never worry about that. So that's the standard deviation we use. Right? So next time I see you, make sure that you remember how to do that, and then we'll talk about how we apply it to the questions in the book and properties of standard deviation.